Hello, my name is Breanne Retherford, and I'm from the Early Back and Medical Devices Center at the University of Minnesota. Today, I'll be presenting on the design and implementation of a targeted cardiocerebral extracorporeal membrane oxygenation system. Sudden cardiac death is the largest cause of natural death in the United States every year. It's currently treated by CPR, which is unreliable, leading to a survival rate of less than 10% out of hospital and less than 20% in hospital. Currently, extracorporeal membrane oxygenation, also known as ECMO, has been proven to increase survival rate through external oxygenation. However, current ECMO solutions require specialized teams and equipment, which restricts the treatment to the most well-equipped and best-staffed hospitals. We will now propose a design which consists of a combination of ECMO and the intra-aortic balloon pump technologies into a new system known as the Targeted Cardiocerebral ECMO, or TC-ECMO, to improve survival rate from sudden cardiac death and potentially risky procedures. Our device modifies current ECMO technology to increase access and use and combines it with the intra-aortic balloon pump that decreases the cardiac workflow by inflating and deflating a balloon to assist in the pumping of the heart. We believe these changes will improve treatment and expand the potential applications of the device. Instead of oxygenating blood for the entire body like in CPR, TC-ECMO targets the brain and vital organs, which allows it to oxygenate more effectively. The device consists of two balloon catheters, venous and arterial, that are connected to an external ECMO machine with a semi-automated oxygenator and pump. The patient is first catheterized with the venous balloon catheter and an arterial pressure sensing catheter. The sensor at the tip of this catheter reports pressure data from the aorta back to the control unit. Deoxygenated blood concurrently moves out of the patient via the venous balloon catheter and into the CardioHealth ECMO machine, where it's oxygenated again. The heart rate and mean arterial pressure data determine the inflation-deflation rates of the balloons and the operational mode. There are three operational modes for TC-ECMO system, each of which is activated and controlled by an Arduino Mega microcontroller. The first mode is for the case of no heartbeat with a low mean arterial pressure, in which targeted support is activated and both balloons are inflated, and the brain and vital organs are perfused with the ECMO system. The second mode is for when the patient retains some cardiac function but still needs significant support. The venous balloon catheter deflates while the arterial balloon catheter oscillates in the same manner as the intra-aortic balloon pump to reduce cardiac workflow. The third mode is for when a patient retains additional cardiac function. In this case, both balloons are deflated and the ECMO is used to provide oxygenation support. Several design considerations distinguish TC-ECMO from current technology, including a custom inflation unit, smaller catheters with an added balloon and pressure sensor, and simple electronics to directly connect, calibrate, and maintain the pressure sensor. In order to precisely inflate and deflate the TC-ECMO catheter balloons, we designed and built a custom inflation system consisting of a stepper motor-driven piston. The stepper motor drives a timing belt and a pulley system, which is used to oscillate the piston back and forth. The piston shuttles a small amount of helium in and out of the catheter balloon very quickly. Two mechanical stop switches were installed, which limit the pulley drive within the confines of the piston. The electronic component of the TC-ECMO system consists of a stepper motor driver, power supply, pressure sensor, and pressure sensor amplifier circuit, all controlled with our Arduino Mega microcontroller. We constructed a custom amplification circuit for precise, fast sensing using the microcontroller. Our analog circuit leverages use of the analog to digital converter on the microcontroller. Finally, the mechanical end switches were to balance with the resistor capacitor circuits. The arterial and venous catheters were constructed to have dual coaxial lumens to maximize flow rate of blood through the inner lumen, optimize helium flow through the outer lumen to provide quick enough balloon inflation and deflation, and minimize outer diameters for easier insertion. Both the arterial and venous catheters have outer diameters of 15 French, which are much smaller than those of typical ECMO, which consist of 23 French and 33 French arterial and venous catheters, respectively. Currently, this device is focused on supporting core functions performed using a number of off-the-shelf materials. Future versions would include system software improvements and custom materials to further optimize performance. This device has been tested in a swine model, appropriate changes are being made, and a second round of animal testing will be performed this year to further solidify the feasibility and performance of this device. With only 1 out of 10 people who experience cardiac arrest outside the clinic surviving, and only 2 out of 10 surviving in the clinic, there's a great need for an increase in accessibility and reliability of treatment that TC-ECMO is designed to address. Thank you for having us participate in DMD 2021, and thank you all for watching.